Okay, let's do some work. Chapter 5 is a pretty long chapter. Deals with a couple new concepts in physics. A lot of the problems are going to be similar, but we're asking different questions about a system. And one of the first things we're going to look at is what we call work. So if you push on an object and it moves, you did work on that object. Right? That's our definition of work. So applying a force causing an object to undergo a displacement is work. Right? And we define work as the product of the force vector and the displacement vector. But this is a unique mathematical operation. So for the sake of those who haven't taken a math class where we've seen this before, just want to introduce what we call the dot product, also known as the scalar product. Alright, so I have two vectors, u and v, and there's an angle between them. Right? We're going to look at all the cases for different angles today. But there's an angle between these two vectors. We've added vectors before, we've multiplied a vector by a scalar, but we haven't multiplied two vectors before. And so the dot product, we use the dot symbol here. The dot product of u dot v is the product of their magnitudes times the cosine of the angle between them. Alright, so this is a new mathematical definition that we use for work, because work is the product of two vectors, the force vector and the displacement vector. So if I know how far an object moved, and I know the force that caused it to move, I can use this formula, FR cosine theta, to calculate the work done. Alright. So what causes this object to move? It's the force, yes it is, but it's the component of the force that's in the same direction or along the same dimension as the displacement. Right? So let's say this was your object, and then you had a force vector in this direction, right? But it's on a surface and it moves in the x direction like this, right? So it undergoes a displacement delta x. The force is in this direction. This component of the force, right? See how it's got an x component, it also has a y component. This component of the force is what's causing the displacement. So this vector is actually f cosine theta, right? If you look at this triangle here, right? We've got the x component of the vector, y component of the vector. This is f cosine theta. So you can think of it that way too, right? F cosine theta, this is an expression for that vector. Alright. So what I like to do is just handle this formula in its purest form and not get too bogged down in that idea, but it kind of helps me visualize what's causing the object to move. Right? It's this component of the force vector. Okay. So work is in joules. We have to define a new SI unit. If you remember from your chemistry time, you probably use calories or kilocalories, something like that for energy, but sometimes you've used joules before. Alright, so a joule is a Newton times a meter. Right? A force times a displacement, Newton meter, is what we call a joule of energy. Okay. Now work can be positive or negative. Work is a scalar, right? See how it's a magnitude times a magnitude times a trig function? This is a scalar. It doesn't have a direction anymore. Okay, so work is a scalar component. Joule is a unit of energy, right? Energy is a scalar. It doesn't have direction. But it can be positive or negative. Right? This depends on the relationship between the applied force direction and the displacement direction. So I'm going to go through a couple cases that will change the value of the work done on an object. So typical cases here, right? We've got a force that's in the direction of the displacement, right? Or maybe it's like this right here, where there's some component in the y direction, but there's a component in the x direction. All right. If you take a crate or a box, some object, and you push it in the x direction, you slide it across the floor, that's this case right here. You're applying a force in the x direction, the object is being displaced in the x direction, the angle between your force vector and the displacement vector is 0. Cosine of 0 is 1. So work is just the magnitude of the force vector times the magnitude of the displacement vector. Alright, so you would get a positive value here. Let's say we had a force that was perpendicular to the displacement. We'll see this a couple times. So if you've got a force that's in the y direction and an object is being displaced in the x direction, there is some force causing it to move in the x direction. But this force in particular we're dealing with is a force that's acting in the y direction. These two vectors are perpendicular to one another. The angle between them is 90 degrees. Cosine of 90 degrees is 0. So the work done by this particular force vector is 0. Again, that's not to say that there isn't going to be another force causing this object to move, but this particular force does 0 work on the object. And then our third case is when the force is in the opposite direction of the displacement. The angle between these two vectors is 180. The cosine of 180 is -1. Alright, so work is going to be the magnitude of the force vector times the magnitude of the displacement vector times -1. Right, so that's negative work. So think of a force that we've seen so far that acts opposite the displacement of an object, and you'll recall that friction forces do this. Right? If you're pulling an object along the surface, friction is going to oppose that motion. Okay? So your applied force pulling the object in the positive x direction is doing positive work, but the friction force is doing negative work. Right? So these are going to be our most common cases. Right? You'll see some forces acting at angles. So use the formula, make sure you measure the angle between the force and the displacement vector correctly. Just calculate it. And you'll get the work. So let's talk about two types of forces. We've got conservative forces and non-conservative forces. There are many different types. I'll talk about the common ones that we see and why they are important. A conservative force does not depend on the path of the object. Doesn't depend on the path of the object. All right. So whether an object travels in a straight line or it travels a curved path, a conservative force does work on it regardless of its path. Okay, so some examples are gravitational force and the spring force. We'll talk more about the spring force later. Okay, so if work is being done by a conservative force, there's a change in potential energy. Right, again, we'll talk about different types of energy. We'll introduce a spring force later. All right. So conservative forces are independent of the path of the object, and it causes a change in potential energy. A non-conservative force, our most common example is friction. Okay. A non-conservative force does work on the object, and the work that it does is dependent upon the path. So take an object and scoot it across the table along the lines of this blue arrow. Okay? Let's say you slide it a foot across the table. So that friction does work on that object that depends on how far it went. If you take that same object, same starting point, you move it up the table, across the table, back down, it traveled a much larger distance, so friction actually did more work on this object because it took a longer path. Okay, so it does more work because the path is longer. So it's not just dependent upon its final and initial position, it depends on the path that it takes. Okay, air resistance is another common one. We neglect that very often, but it's dependent upon the path that it takes. Okay, so friction is an example of a non-conservative force. Gravity and the spring force are our most common examples of conservative forces. So let's start off with a work problem here. Pretty straightforward. We have multiple forces acting on this sled, right? Somebody's coming back from a fishing trip. They've got a sled. They're applying a force in this direction, right? So we've got an angle theta. This person is pulling the sled, applying a force at this angle. There's a normal force. There's the gravitational force, and then there is friction. All right, we're given the frictional force, I believe, right? So we're not given the coefficient of friction, but we just have the value of the friction force, so we don't have to calculate it. That's very nice. All right, so my free body diagram, I've got my applied force, normal, gravity, friction. So they're asking how much work is done on the sled, right? This is a little typo. This says as it is pulled 5 meters. Okay. So we're looking for how much work is done on the sled. We've got the angle of the applied force. We've got the magnitude of the applied force. We've got the mass of the sled, so we can calculate the gravitational force. And then we've got the value of the frictional force. And we have the displacement, 5 meters. Okay. So I'm going to take the work due to all of the individual forces. This is similar to a WebAssign problem too. There's going to be an object in motion, and then they're going to ask you for the work done by each specific force. So that's why I'm doing this here. So I want the net work, right? I want the total work done. So I'm going to calculate the work done by all 4 forces, and then add them together. So let's start with the applied force first. F applied is acting at an angle, right? So I'm going to use F dot delta R. The magnitude of the applied force, 120 newtons. Notice I'm not splitting it up into X and Y components. I'm just taking the magnitude here. 120 newton magnitude of the applied force, 5 meters is the displacement. The angle between the displacement vector and the applied force vector is 30 degrees. All right. Put that in my calculator, I get 520 joules of work. Remember, Newton meters, that's a joule. 520 joules of work, it's positive. The component of the force that's causing the displacement is in the same direction as the displacement. So we've got work due to the applied force, good. Let's calculate work due to the friction force. I've got the magnitude of the friction force given to me. All right. If you're not given this, you'll be given a coefficient, and you'll be able to solve for the normal force. All right, but we're just given the value of the friction force now, which is nice. Magnitude of the friction force, magnitude of the displacement, angle between them. Friction force is in that direction, delta R is in the opposite direction. So the angle between them is 180, cosine of 180 is -1. Again, like I said before, friction is doing negative work. So negative 225 joules. What about work due to the normal force? Normal force, displacement. I don't even know what the normal force is, but you know what? I'm not going to spend my time trying to calculate it, because I know the angle between the normal force and the displacement vector is 90 degrees. Cosine of 90, 0. The work does 0 joules of work. Same thing with gravity. The angle between the gravitational force vector and the displacement vector is 90. Cosine of 90 is 0. Gravity does no work on this object. So I didn't even have to calculate the normal and the gravitational force, because I know both of those were perpendicular to the displacement. So they're doing no work, 0 joules. Add the work up, 520 joules minus 225 joules. I've got a total work done of 295 joules. Again, work can be negative, so watch out for that. Just use your formula. Make sure you identify the appropriate angle between the vectors, all right? And that'll tell you whether it's positive or negative. All right, so another similar example, except the applied force is in the direction of the displacement. So the mass of the crate is 100 kilograms. It's being pushed, right? So it's being pushed at a speed of 1 meter per second. right? So it's moving at a constant speed, but it hits this spot right here, and this length L, this is a rough surface, so it's going to encounter a surface that has a coefficient of friction, and it's going to experience a frictional force in the negative x direction. Okay, this person is applying a force of 400 newtons. All right. I've got the coefficient of friction, between the block and the surface. So I want the magnitude and direction of the net force on the crate while it's on the rough surface. Now what I did was, I believe I found the individual forces first in the x direction, so I may not have actually added them up, so I'll double check my solutions and then we'll get a solution there. So I'm going to find the magnitude and direction of the individual forces, add them up, then I'm going to find the net work done. So I'm going to find the work due to each individual force, add them up just like I did the previous problem. Final part, find the speed of the crate when it reaches the end of the rough surface. So I think I'm probably going to have to use like Newton's second law, probably have to find an acceleration. I've got an initial speed, and then I'll probably have to use kinematics to find a final speed, right? Because I've got a displacement of 2 meters. Right? So this is a nice problem, right? Because it's got some chapter 5 stuff in there. It's got some old kinematic stuff in there, which is nice, but it's got a work problem in it too. Okay. So I got a free body diagram: applied force positive x, normal force positive y, gravity negative y, friction negative x. Friction is mu times the normal. What's the normal force? Let's skip down here a second, right? I've got normal minus gravity, very common case, very common occurrence here. Normal minus gravity is 0. It's not accelerating in the y direction. So the normal is equal to the weight force, mass 100 kilograms, g. I get a weight force of 980 newtons. The normal force is 980 newtons. Now that I have the normal force, I can calculate the frictional force, multiply the normal force by 0.3, and I get a frictional force of 294 newtons. Now this is acting in the negative x direction. Again, I'm just writing down the magnitude. I'm just writing down the value. So the applied force is 400 newtons, and so that's what I missed, I think, right? Find the magnitude and direction of the net force on the crate while it's on the surface. So that answer is actually 400 newtons, which is the applied force, minus the frictional force, right? So in the x direction, I've got 400 newtons minus 294 newtons. So the net force is 106 newtons. All right, so that's the first part. Now I'm going to calculate the net work, right? Find the net work done. So I'm going to find the work due to F applied and the work due to friction, and then add them up. Similar to the previous example, I know the normal force isn't doing any work because it's perpendicular to the displacement. Same thing with gravity. Perpendicular to the displacement, 0 work done by normal and gravity. So let's calculate the work due to F applied. 400 newtons is the magnitude of the applied force, 2 meters is the displacement. The angle between these two vectors is 0. The person is pushing in the positive x direction. Alright, so there's no angle between these two vectors. So it's just force times displacement, 800 joules. Work due to friction. Frictional force, I found that. Same displacement. The angle between the friction force vector and the displacement vector is 180. Friction again is doing negative work. That's negative 1 F times delta R, negative 588 joules. Add the work due to the individual forces, 800 minus 588 joules, and I get 212 joules. Okay. So that's the net work done. Now it's time for Newton's second law, which I already wrote out. It's very good, very handy to have. I'm going to use this to solve for the acceleration, and then once I have the acceleration, I'll use kinematics to find the final speed. Right? So divide both sides by m. I've got the applied force, know that. Frictional force, know that. Mass of the crate, know that. I can plug everything in and I get an acceleration. It's positive, which is good, okay? And that makes sense too, because the applied force is greater than the friction force. So I've got a net force in the positive x direction. I've got an acceleration in the positive x direction. So that's good. 1.06 meters per second squared is what I got. I'm going to use this kinematics equation because I've got the displacement along the rough surface. I was given the initial velocity and I have the acceleration. Take the square root of both sides, plug my values in, and I get a final velocity of 2.3 meters per second. Okay. So dot product for work, make sure you identify the angles between the two vectors, and then let your equation do the heavy lifting. But watch out for some old chapter 4 stuff in there too, right? You still got to do free body diagrams to find other information, right? Newton's second law. Some kinematics are going to make their way back into these problems. Okay. So I'll do just a couple of these, and then I'll take a break. I think I'm getting to like 20-30 minutes or so here. So I'll do these work problems, and then I'll pause it, upload it, and make another video, probably another couple videos for chapter 5. Like I said, it's pretty long, and I'll try to keep them short. Again, like I said, forces aren't always constant, right? Forces can change with time. They can change with an object's position. So the best way to handle that is if you're given a graph, right? If you're given a force displacement graph, if you notice, my y-axis is my force, my x-axis is my displacement. And so we see that this force is increasing with the object's position, right? It starts at 0 and it increases, in this case, linearly. All right, it increases linearly with position. So I want the work done, but I can't just take this force, because it's not a constant value, and multiply it by the displacement. So I have to interpret this graph. Now, the work done by a varying force is the magnitude of the average force times the displacement. Now, if I have this force function, this is a function, right? It's a linear function, but it's a function nonetheless. Right? So it's actually the area under the force displacement graph, or the force position graph. Okay, so see this highlighted region right here? The area of this triangle here is the work done by this force. Now, if this were like a quadratic, or some curvy graph, or like a trig function or something, we'd have to use calculus, right? We'd actually have to integrate the force function over some initial and final displacement. I'm not going to ask you to use calculus. This is an algebra-based course, but those of you who have seen calculus might find this a little bit familiar, right? So I'm just taking the area under a curve. So I would integrate the force function, right? And I would give it boundaries, initial position, final position. All my graphs are going to be nice and linear, and I'll actually just be able to use geometry and take the area of the shapes and calculate the work done that way. Right? So let's do this one. The highlighted region is the area under the force function, right? It's the region bounded by the force function, the initial and the final position, right? Say x equals 0, x equals 7 meters, and the x-axis, right? So this highlighted region, the area of this region is the work done. So it's a triangle. Area of a triangle is 1/2 base times height. The base of this triangle is the change in position, right? 7 meters. 7 meters minus 0 meters. So the base of this triangle, it represents a physical quantity, so it has units, right? It's 7 meters. The height of the triangle is the force applied here, 80 newtons, right? The height of this triangle is 80 newtons. The base of this triangle is 7 meters. So I'm in units of work, which is good, right? Newton meters is a joule. So 1/2 base times height. I get 280 Newton meters, 280 joules. Right? So if you're given a force displacement graph, all you need to do is take the area under that graph, whether it be a rectangle or a triangle or some combination of the two, find the area under that curve, and you've got the net work done. Second slide is one of those problems, right? We've got linear functions, right? This is a linear function. This is actually a constant force, right? So a constant force of 80 newtons over the first 5 meters. And then from 5 meters to 10 meters, the force immediately drops down to 40 newtons and then decreases linearly to 0 newtons. Now this isn't a shape that I can immediately take the area of, but I can split it up into two parts. So I'm going to take this line right here, this vertical line, draw it all the way down to the x-axis, and I'm going to split this up into a rectangle over here and a right triangle over here. So I'm going to take the area of this rectangle, the area of this triangle, and just add them up. So the rectangle has a height of 80 newtons, and it's got a base of 5 meters. It's a rectangle. Don't put the 1/2 in there because it's a rectangle this time. So it's the force, 80 newtons, times the displacement, the base of the rectangle times the height of the rectangle, 80 newtons times 5 meters, 400 joules. The second part of the graph is a triangle. It's got a height of 40 newtons, also has a base of 5 meters. 10 meters minus 5 meters is 5 meters. Okay, it's got a base of 5 meters. It's got a height of 40, but it's a triangle. So it's 1/2 the base, 5 meters again, times the height of the triangle, 40 newtons. That's 100 joules. So the total work done by this force on the 5 kilogram object, don't need the mass of the object in this case, is 400 joules plus 100 joules, 500 joules. In the event that you ever see a graph where the force function is negative and it's below the x-axis, right? You've got a negative force, maybe due to friction or something like that. Any area that's under the x-axis made by the force function is going to be negative. So just watch out for that. If you're under the x-axis, that's a negative force. All right? So I'm going to encode this, upload it, and then I will pick back up with slide 10 in the next video. All right, thanks.